Okay, the next part of the lab is on frictional forces. So let me go back over to the iPad and describe friction and frictional forces. Okay, so first situation, let's say we have an object, it's on a flat surface. So we're gonna have like a wooden cart, right? That's gonna be on that wooden track, which is gonna be kept horizontal, so it's a flat surface. And let's say I exert a force to the left, so I pull on it with some force F. Let's assume that the cart is not moving, so not moving. Well, because it's not moving, right, the acceleration would have to be zero, which means the net force would have to be zero. So there must be some force that's resisting the motion that's pointing toward the right. And actually it has to have exactly the same magnitude as F, but going towards the right. So I'll draw it the same length. And this is what's called a static frictional force. So we call it F sub S. So it's a static frictional force. And then if I pull harder, so again, let's assume it's still not moving. So this object, the box or the cart is not moving. Let's say I pull harder now. Then it turns out that static frictional force is going to increase to balance out the force I'm pulling with. Because again, the net force would have to be zero, right? If I add those two up, I have to get zero because it's not moving, it's not accelerating. And you can keep doing this until the object is on the verge of motion. So I'll say on verge of motion. So let's say I pull really hard now to the right with the force F. Then again, there's a static frictional force that's resisting it because it's still not moving, although it's right on the verge of motion. If I pulled any harder, it would start moving, but it's still not moving yet. So I still have a static frictional force. But because it's the largest that the static frictional force can be, we call this Fs max. So Fs max, it's like the maximum static frictional force. Okay, and notice that the static frictional force can increase from zero, like if you're not pulling at all, there's no static frictional force, all the way up to Fs max. So that's why you'll see the static frictional force defined to be Fs is greater than or equal to zero, less than or equal to Fs max. Right, so it can vary. In this case, it was very small, right? If there's no force at all, this would be zero, right? There'd be no force resisting it, and it can go all the way up to a maximum value. And then the other situation is if I'm pulling on the cart, let's say it's moving now, but I'm going to do a special case. Let's say it's moving at a constant velocity. Constant velocity. So if I pull it with some force F and it's moving with a constant velocity, well, again, if it's constant velocity, that means there's no acceleration. So the net force has to be zero. So what's the force that's resisting it in this case? It's a type of frictional force. And since it's moving, we call this a kinetic frictional force. So this is called F sub K for kinetic. So kinetic is when it's moving, static is when it's not moving. And in this particular example, the magnitude of F, if I calculate what that magnitude is in newtons, that's going to be the magnitude of my kinetic frictional force. Why? Because it's moving at constant velocity. It's not accelerating. So the net force, if I add those two together, it has to equal zero. Okay, now there are some models for frictional forces, and it turns out that you can model Fs max and Fk as being proportional to the normal force. And what the proportionality constant we usually use mu. So for the static frictional force, we use mu s, and it's times the normal force. So it's proportional to the normal force. So this mu s here is the coefficient. Let me make some room here. This is the coefficient of static friction. And the n here is the normal force. Normal force. Okay, now that these coefficients, these are just numbers, right? They represent something about the two surfaces that are sliding over one another. In this lab, it was a wooden cart that had these leather straps on the bottom, and it was sliding on a wooden ramp. So really, we were looking at the friction between the leather straps and the wooden ramp, right? So there was some coefficient that defined the maximal static frictional force. And then for the kinetic frictional force, there's a similar relation, except it has its own coefficient called mu k times the normal force. And this mu here is called the coefficient of kinetic friction. Okay, so actually what I want to do now is I want to remind you what normal force is, right? So in this example, it's actually really straightforward. If I have the cart on a flat air track, or sorry, not a flat air track, a flat wooden track, right? Because it's sliding on a wooden track. So a cart on a flat wooden track. Well, there's only two forces acting in the vertical direction, right? I have the weight acting down to vector, it's equal to mg. And I have, in this case, the normal force is the force that the surface exerts on the object perpendicular to the surface. So the normal force is acting up in this case. And then if you applied Newton's second law to the y direction, and there could be other forces acting on the x direction, I won't draw them right now. Let's assume it's just sitting there. So if I look at the sum of the forces in the y, that's got to equal MAY. So in this case, I want the y component of the normal force plus the y component of the weight. That's got to equal MAY. But the y component of the normal force is, since it's all in the y direction, right? If I call this my coordinate system, this is say y, and this is x, then all that normal force is in the positive y direction. So this is just positive n. And then the y component of the weight is actually minus mg, right? Because it's acting in negative y direction. And that's equal to 0 because it's not accelerating in the y direction. That wooden cart is not leaving the wooden ramp at all. And then, of course, we can solve for n now. And it turns out n in this case is simply equal to the weight, right? The weight of that wooden cart. Now, this isn't always necessarily the case, right? When the ramp is on an incline, the normal force is definitely not equal to the weight. It's only equal to a portion of the weight, right? So it's more complicated. But in this case, when it's on a flat surface, there's no other forces acting in the vertical direction than the y direction, then the normal force is equal to the weight. So that's going to be true for this part of the lab. The normal force will just be equal to the weight. All right, now which force is larger, right? So if you look at the maximal static frictional force or kinetic frictional force, which one is larger? Well, let me give you sort of an everyday example. Let's say you're trying to move a large piece of furniture, right? Is it harder to initiate the motion, like right when it's on the verge of moving, or is it harder to move it while it's sliding already? Is it harder to get it started or to push it while it's already sliding? And it turns out, probably from experience, you guys have experienced this, right? That it's harder to initiate the motion, right? So it turns out that Fs max should be should be greater than Fk. So the maximal static frictional force should be greater than the kinetic frictional force. And that in turn implies that the coefficient of static friction must be greater than the coefficient of kinetic friction. Okay. And really in lab today, in this lab, we're going to measure the coefficient of static friction and the coefficient of kinetic friction. That's sort of the goal for this particular lab. Okay, let me go back to the handout. Okay, so make sure you watch my video, my quick little short video on how the data was collected for this particular section. Basically, what we did was we used a force sensor, right? And we pulled on the cart. And initially, right, you're pulling harder on the force sensor, but the cart's not quite moving. And at some point it gives. So the highest force is going to be the maximal static frictional force. And then we keep pulling the cart, but now at a constant velocity. And then that force that we're recording from the sensor is going to be equal to the kinetic frictional force. Okay, actually, let me go back to the iPad for a second to show you what this graph looks like. And you can also look at that video. If you look at the second video here, here's where I analyze Fs max and Fk from the graph of force versus time. But let me just show you this quick on the iPad. Okay, so if we plot force in newtons versus time in seconds, when I'm pulling on the cart, right, with that force sensor connected to it, at first the cart is not moving, but the force is going to be increasing, something like this. It'll reach a peak, it'll drop, and then now if I pull with constant velocity, it kind of plateaus, maybe something like that. And then when I stop pulling, the force goes back down to 0. So basically, here's where, dividing line here. This is where the cart is not moving. So the force is increasing, but the cart's not moving. And here, after that red line, is where the cart is moving at a constant velocity. I'm pulling it at a constant velocity, that wooden cart. Okay, so how do I get those measures of Fs max, the maximal static frictional force, and the kinetic frictional force? Well, the peak of this graph right here, that peak, that is Fs max. So when I did that graph, I found the peak of the graph. And then sort of the average of this plateau, somewhere in here, right, the average of that, that's when I'm pulling at a constant velocity, that's Fk. Because remember, the force I'm pulling with has got to be equal to the force of friction that's resisting the motion, the kinetic frictional force, because there's no acceleration. I'm pulling at constant velocity. So that's Fk. So that's how I got those two values, Fs max and Fk. Okay, so now that you saw the background information on frictional forces, let's talk about the lab itself. So for this part of the lab, let me go down to here. It's basically question 13 is what you want to answer from your lab manual. And what you need to do is you need to fill in these data tables. And then ultimately you need to do 2 plots on Pascal capstone. Okay, so let me go over what's in these tables first. So these are the 4 conditions, right? Remember, it was like it's the cart with 2 weights is the first condition. Then there's a little bit heavier, the wooden cart with 3 weights, wooden cart with 4 weights, wooden cart with 5 weights, right? So those are the 4 conditions. One of the things that we need is we need to know the mass of the cart in kilograms, right? So you can either get that from, again, if you're watching this because you couldn't attend lab, you can get this information from your lab partners. Or if you, for some reason, can't, just contact me and I can give you some data for this, so the mass of the carts. And this will be the same for both of these tables. Okay, once we have the mass of the cart, how do we compute the normal force? Remember, the normal force is the force that the wooden ramp, which is horizontal, exerts upward on the cart, right? So it's a force that's perpendicular to the surface. So in this case, it's the upward force. Well, the downward force is actually the weight of the cart, right? And the weight of the cart is simply going to be the mass times gravity to calculate it. So the mass in kilograms times 9.8. However, since there are no other forces acting in the y direction, the normal force is simply equal to the weight. And I have that here in this note here. So normal force is simply going to be equal to the weight in this case, which is the mass in kilograms times 9.8. So that's how you calculate your normal force. And again, that'll be the same for both of these tables here. Now, the Fs max and the Fk, remember, this is the information that comes from using the force sensor and reading off these values from the graph, right? From the data logger, from the GLX device. So these are values that, again, you're going to have to get from your lab partner or contact me if you want, if you can't, for some reason, can't get the information from your lab partners. Okay, so question 13. What you need to do is you need to make a graph of Fs max versus normal force. So that's the first graph. So Fs max is going to be on the y-axis, normal force on the x-axis. All right, let me jump over to the iPad just to show you this real quick. Okay, so in this case, we're going to be plotting maximal static frictional force on the y-axis. So I'll call it maximal static frictional force. That's in newtons versus normal force on the x-axis. It makes sense to include 0, 0, so you should also include 0, 0 as one of your data points. And then the question is, what is this graph going to look like? Well, remember the equation for Fs max, the maximal static frictional force, it's equal to μs times the normal force. So if we plot Fs max on the y-axis and normal force on the x, this is basically a linear equation, right? This is kind of like y equals mx plus b, where b is 0 in this case. So if you, when you do your plot, it should look pretty much linear. So let's say these are your 4 data points. You want to do a linear fit. Okay, so do a linear fit. And the slope is going to be really important. Remember, it'll give you the slope. What does the slope represent? Well, the slope is going to be μs, right? So y is like our Fs max because I plotted that on the y-axis. My x is basically the normal force because I plotted that on the x-axis, normal force. So the slope here corresponds to μs. So this slope is just a way of getting μs. And then the second graph is very similar, except now you're plotting kinetic frictional force versus normal force. So in the second graph, you're going to plot kinetic frictional force which is in newtons versus normal force. The newtons, again, include 0, 0. Remember, in this case, the equation is very similar. It's Fk equals mu k times n. So this should be linear again. Let's say this is your data. You want to do a linear fit. And in this case, the slope is equal to the coefficient of kinetic friction, right? Their slope is equal to mu k. Okay, so basically question 13 is to plot these two graphs and then record those two values, mu s and mu k. In fact, this value is really important in mu k because you're going to need this for the last part of the lab where the cart is being pulled up an incline. So you'll need that mu k value. Great. Continue watching. There's one other part where we're going to look at the frictional force when the cart is on an incline. Okay. Okay, so in this part of the lab, we have the cart, which is now on the incline wooden track here. And the wooden track is going to be set at several different angles. Actually, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 65, 70, 75, 80, all the way up to 85 degrees. We're going to keep raising it. And the cart has just a single square mass on it, right? So it has one particular mass, and that's going to stay the same for all these different conditions. The conditions are these different angles. On the other side, so we have the string attached to the cart. It goes over a pulley, and then we have a suspended mass here. Now, what I did was I adjusted the mass on the suspended mass, so how much mass I put on there, such that when I gave this a little tap to basically to overcome the static frictional force, the cart moved with like a constant velocity up the ramp. Okay, so it's not accelerating. We're purposely adjusting the mass so that when we give this a tap, it moves at a constant velocity up the ramp. And we do that for each of the different angles, right? So we have to keep adjusting this mass, tap this cart, and it's going to move at a constant velocity up the ramp. And the idea is to calculate the tension two different ways. To calculate it experimentally means analyzing the suspended mass. Now, if you look at the suspended mass here, right, there's two forces acting. You have a tension acting up, right, the tension in the string acting up. You have the weight of the suspended mass acting down. However, if this cart is moving at a constant velocity, so there's no acceleration, that means the suspended mass is also moving down at a constant velocity with zero acceleration. Since there's no acceleration, that means the sum of the forces in the y direction has to equal zero. Therefore, the tension is going to be equal to the weight. So if I know what mass is on here in kilograms, I can just multiply by g by 9.8, and that gives me the weight, but that's the same as the tension. So that's how we find the experimental tension. In fact, that's in the table here. To get the experimental tension, these are all the masses I had to put on there so that it moved at a constant velocity. So you're simply going to multiply these by 9.8, and that will be the experimental tension. Now, the theoretical tension is more complicated, right? So in theory, we should be able to calculate what this tension is pulling on the cart based on the information that we have from the cart. Okay, so actually, let me do that right now. So I'll try and derive this formula, and I'll do it on the iPad. Okay, so here's the situation, right? I have the ramp. It's at some angle. Right? Remember, we're going to vary that angle theta. You should really watch the video to see how I collected this data. And then there was a pulley. So a pulley over here. And then that wooden cart with the one weight was on the ramp. And we had a string connected to the cart. And then on this side, we had a suspended mass. And the idea was to adjust the mass, right? Adjust this suspended mass. This is like, think of this as M2. Adjust M2, this was M1, such that the cart moved up the ramp at a constant velocity. The idea was to move it up at a constant velocity. Constant velocity. Okay, and what I want to do is I want to figure out the tension, right? The tension in the string. So theoretically, what should that tension be? So let's look at all the forces acting on that cart. Let me draw this more carefully. So this is the ramp. This would be the angle theta. And this is my cart, right? So there's several forces acting on it. I have the weight, which is acting down. So that's the gravitational force. I'll call this W1, right? So it's M1G. I have a normal force, which is perpendicular to the surface, so perpendicular to that wooden ramp that's acting up. And then we had the tension that was pulling parallel to the ramp, right? That was a string. And then also, since it's moving, right, at a constant velocity, or it doesn't even matter if it's moving at all, it has a kinetic frictional force. So we have a kinetic frictional force in this direction, Fk. And remember, Fk is equal to mu k, that coefficient, which we know from earlier, right? Because we found that coefficient when we did the graph. Actually, we found it twice, but we're going to use the one where it was the slope of the graph where we plotted the kinetic frictional force versus the normal force. We know that that kinetic frictional force is mu k times the normal force. Okay, so first thing, create a coordinate system. Well, in this case, since it's moving along the ramp, I'm going to call that the x direction. I'll just call down positive. It doesn't really matter in this case, even though it's moving up, but that's fine. And then perpendicular to it will be y. Okay. And then if you notice, all the forces act along the coordinate system except the weight, but I can fix that, right? Let me find the components of the weight. So I'm going to resolve this into the y component of the weight, which is like this, wy, and then the x component of the weight, which is like this. That'd be wx. And remember, this angle theta that the ramp makes with the horizontal, it turns out that's exactly the same as this angle theta. Okay, so first thing, let's figure out the x and y components of the weight, what those are. So let me extract out that right triangle here. Okay, so remember, this is theta. This was wy. This is wx. Right? It's really w1y, w1x. I'll just call it. Let me put a 1 in there just to remind it it's 1. Okay, so w1y, w1x. And then the hypotenuse here is going to be the magnitude of that force, which is the weight. So this is just m1g, right? That's the magnitude of the weight. Now notice that relative to the angle theta, w1y is adjacent, right? And m1g is hypotenuse. So what trig function relates adjacent and hypotenuse? That would be cosine, right? So katoa, so ka is adjacent over hypotenuse. So we know that cosine of theta is equal to the adjacent side, w1x, divided by the hypotenuse, m1g. So therefore, I can solve for w1x, and it's going to be m1g times cosine of theta. And then w1x is, oh, hold on a second. I made a mistake there. This should be w1y, right? The y is adjacent to it. So this is y, w1y. And then opposite the angle theta is w1x, right? So this is the y adjacent, this is the x opposite. So what relates opposite to hypotenuse? That's sine, right? So I know that sine of theta is equal to w1x divided by m1g. And if I solve for w1x, it's going to be m1g sine of theta. Okay, so we have those two components. All right. Now what we're going to do is apply Newton's second law to this situation. Let me bring up the picture again. So let me first apply it in the y direction. So I have the sum of the forces in the y direction equals m1 ay. So I want all the y components, right? I want the y component of the normal force. I want the y component of the tension. I want the y component of the weight, and I want the y component of the kinetic frictional force. And that's got to equal m1ay. Well, what is the y component of the normal force? So if we look at the normal force, right, here's the vector. All of it is in the positive y direction, right? So the y component of normal force is simply going to be all of m, right, the entire magnitude. What's the y component of the tension? Well, if you look at the tension, it's acting along the negative x direction, so none of that vector is in the y. So this is just 0. If I look at the y component of the weight, well, all of it is acting, but in a negative direction. And we just calculated it earlier. It was this, right? W1y is m1g cosine theta. And it's acting in a negative direction, right? So it's negative m1g cosine theta. And then how about the kinetic frictional force? How much of that is in the y direction? None of it, right? It's all in the positive x. So this is plus 0. And we know that this cart is not accelerating. It's not leaving the ramp at all in the y direction. So the acceleration in the y direction is equal to 0. And then if you bring this term to the other side, I can solve this for n. So the normal force in this case happens to be m1g cosine theta. It's m1g cosine theta. Okay, now let me go to the x direction. So in the x direction, I have sum of the forces in the x equals m1ax. So again, I want the x component of the normal force, the x component of the tension, the x component of the weight, and the x component of the frictional force. That's got to equal m1ax. Well, what's the x component of the normal force? Well, since the entire normal force is in the positive y direction, none of that vector is in the x. This is 0. What's the x component of the tension? Well, I look at the tension vector. It's acting to the left. Remember, I called positive x to the right. So it's acting in a negative x direction, all of it. So this is going to be negative t, right? The entire tension. What about the x component of the weight? Well, remember that was acting in the positive x direction, and we calculated it here. It was m1g sine theta. So this is plus m1g sine theta. And then what about the frictional force? Well, it's also all in the positive x direction. But remember, it's equal to mu k times n, right? The frictional force is mu k times n. So this is going to be plus mu k, and in n we just found from above, it's m1g cosine theta. Right, it's m1g cosine theta equals, and now what is the acceleration in the x direction? Well, in this case, remember that this cart is moving at a constant velocity, right? We're adjusting the mass on the hanger, so the cart specifically moves at a constant velocity up the wooden ramp. Therefore, its acceleration is 0, right, in the x direction. So this is just equal to 0. Okay. Now what I can do is I can solve this for t, right? I want to figure out what the tension is. So basically, I'll add t to both sides. I'll bring it to the right-hand side. And I'm going to get m1g. I'm going to write this. I'm going to rearrange terms a little bit. m1g mu k cosine theta. Right? I'll write that second term plus m1g sine theta. And now since m1 is common to both terms on the right-hand side, let's factor it out. So I get m1g, and I'm left with mu k cosine theta plus sine theta. And that is exactly the equation that we want. So we're calling this like the T theory. This is like the theoretical tension. Okay, so let's go back to the hand. All right, so we just derived this equation, right? So T theoretical is m1g times the quantity mu k cosine theta plus sine theta. So in the table here, what you're going to do is you're first going to compute the experimental tension. Remember that dealt with the hanging mass, right? And since it was moving at a constant velocity, the acceleration was 0. So the tension in the string experimentally was simply equal to the weight of the hanger. So how do I compute that? Well, that's going to be m2 times 9.8, right? And then this one times 9.8, and that m2 times 9.8. So you're going to get all these theoretical, experimental tensions. That'll be this column right here. And then the last column, the theoretical tension, that comes from this equation, right? So you're going to plug in the values. You need to plug in your different angles. For mu k, you're going to use the value from question 11 that came from the slope of your kinetic frictional force versus normal force graph. So use it from, where is it? It's all the way up here, right? So use this value, mu k, from question 11. And then the M1 here is simply the mass of the cart with that one weight, but that stayed the same through all the conditions. So that's just going to be 0.3529 for every condition. And G, of course, is 9.8 again. Okay, then what I want you to do is compare, well, actually, you're going to do 2 plots. You're going to plot T experimental, so tension experimental, this will be on the Y, and angle on the X, okay? And then you want to do a polynomial fit, there'll be some type of curve, and now using the coordinate tool, just like we did in the projectile motion lab, where we had to use that coordinate tool, I'll actually jump on capstone in a second and show you how to do this. You're going to find the peak of the fitted curve, okay? And then that peak will give us basically an ordered pair, and the first value will be like the optimal angle, experimental, and then the maximum tension, experimental. We're getting those 2 values. So actually, let me show you this. So you're going to plot angle on the X, tension, experimental on the Y. Okay, so let's go. The usual, right, you choose classic templates, and then this upper left-hand one. For the x-axis, remember that's going to be angle for both when we plot the theoretical tension and the experimental tension. So this will be angle. For the units, you can either write in degrees, or if you have a keyboard, if you hold the Alt key down and you press 2, 4, 8 in a numpad and lift up the Alt, you'll get a degree symbol, or you can just write in degrees. Either one is fine. And let's say this is my experimental tension. And in units would be newtons in this case. Okay, so remember my angles were like 20, 30, 40, 50, 60, then 65, 70, 75, 80, 85. And then let's say, I'm just going to make up some somewhat reasonable values here. Let's say my tension was 2.40, 2.85, 3.20, 3.45, 3.60, 3.63, 3.63, 3.60, 3.55, 3.47, something like that. Okay, so now we choose angle, right, on the X, and then experimental tension on the Y. Remember, for the title, it's always Y versus X, so you could say experimental tension versus angle. That would be fine. I want to get rid of these line connections. So you hover over data point, right click, uncheck show connecting lines, usual. And now for this one, we're going to do a polynomial fit. So we'll choose fit and go to polynomial. Okay, and it does a fairly smooth fit right through all the data. So what we want to do is we want to find the maximum tension experimentally, which means after I fit the graph, I want to find the peak of my curve. You don't want to use one of your data points. You actually want to find the peak of your curve. And then we want to find the angle at which that maximum occurred at, and we're calling that the optimal angle, experimental. So how do we do that? Just like we did when we did the projectile motion lab and we plotted range versus angle. Remember we used that coordinate tool? So you want to do that here as well. So coordinate tool, go to add coordinates. We have to set it up first. You have to click on it, right click, tool properties, go to coordinates, and then change that snap to pixel distance to a 1, right? Just so it doesn't jump around. And now you should be able to drag this. Ooh, there we go. Drag it to the peak of your graph. Maybe right there. I can move this down a little bit if I want. Maybe right there would be the peak, okay? And then it gives you a coordinate pair, right? And the first value obviously is going to be your angle. So that'll be your optimal angle. And then the second value, that's this value right here, that's going to be your experimental maximum tension, right? So those are the two values that you want. And then the usual, you want to include this graph. Make sure you include this graph in your lab report. So you hover over the border, right click, copy display, and paste it into your group lab report. Okay, so you're going to do two graphs. You're going to do one for experimental tension and one for theoretical tension. All right, let me go back to the handout. Okay, so again, for both graphs, right, theta will be x, and then tension will be y. In the first graph, experimental tension will be y, and the second graph, your theoretical tension will be in the y. So you want to locate, using the coordinate tool, the maximum experimental tension and then the optimal angle, and then do the same thing for the theoretical versus angle graph. Locate the maximum tension theory and the optimal angle theory. Those values will go in this final table here. Okay, so this is experimental, both the tension and the optimal angle, and the same thing for the theoretical graph, tension and angle. And then you want to compare these two by computing the usual percent experimental error, right? Think of the theoretical as the accepted one. So when you compute the percent experimental error, you want to divide by the theoretical one. Make sure you show me all your calculations. So make sure you show me these two calculations here. And hopefully they're close, right? Because in theory, the experimental tension that we got by calculating the weight of that hanging mass, that should equal the tension that we derived from that longer theoretical formula, right? In theory, they should be the same. All right, so that's it for this particular lab. And next time for lab 5, we will actually be looking at different things. So Physics 212 will be looking at work and energy, and the other classes will be looking at torques. Okay, great. Okay, since this is a different semester than when that video was originally recorded, the part of the video that you just watched, the numbering is slightly different for this part of the experiment. So I just wanted to mention that so it's not too confusing. So but the questions are exactly the same. So it's the same exact idea where we're trying to measure the theoretical tension and the experimental tension as the wooden cart is being pulled up the ramp at a constant velocity. The only difference is going to be in the numbering in the questions. Okay, in your lab manual, actually, these questions are question 14, 15, and 16. But everything else is the same. So again, you'll need the mass of the cart. You can either use values from your lab partner, or if you can't get them, I can give you those values. It's the same value, right? Because that stays the same. It's mass of the cart with one weight. So that stays the same for all these conditions, all these different angles. The suspended mass is how much mass you had to put on the hanger such that the cart moves up the ramp at a constant velocity. So these are your experimental data. And again, your lab partners will have that data. If not, I can get you that data. The theoretical tension in the string is simply going to be the weight of the hanger. So if you multiply this mass of the hanger in kilograms times 9.8, right, M2 times G, that's the experimental tension. And then the theoretical tension you can compute. Once you know all this information, let me go back to the formula here. So we derive this formula. You need to know mu k, right? That's why earlier we had to find mu k from the graph, the coefficient of kinetic friction. We need to know the angle. So you're given the particular angles. You need the mass of the cart, M1, and G is 9.8. So if you plug those values in, that would be the theoretical tension in the strain, right? So that'll be this last column here. And then again, you just watched the video, right? The questions are exactly the same. They're just numbered differently. So question 14 from the lab manual is plot, so graph T experimental versus the angle. And then you want to use that polynomial fit with the coordinate tool to find the peak of the graph, right? You want to determine the maximum tension in the string from the graph and the optimal angle, like as I showed. And then question 15 is the same thing, but now you're plotting the theoretical tension on the y-axis versus angle on the x. You're going to do a polynomial fit, and then using the coordinate tool, you'll find the peak of the graph again. So you'll find the maximum tension theoretical and then the optimal angle theoretical. Question 16 is basically to fill in this table. So you can put in those max tensions, experimental and theoretical, in the table, and same thing with optimal angle. And then I want you to compare them. So compare experimental versus theoretical by computing a percent experimental error. And the same thing for the optimal angle. Compare them by computing a percent experimental error. And make sure you show me these calculations. Also, I would show like a couple of sample calculations as well, like how you calculated T experimental and how you calculated T theoretical. Here, you can just show a couple of sample calculations. For this last question, when you compute the error, show both of these percent experimental errors. Okay, great. So again, it's the same exact thing as what was just mentioned in the video, just different numbering in the questions. Okay, then there is a simulation part of this experiment. So let me go to the simulation and show you what you need to do for this part. Okay, so for this part, for the simulation with the friction, we're going to choose friction. We're going to go to the same simulation, choose friction. And then you want to click on all of these. So forces, sum of forces, values, masses, speed. And then what you're going to do is you're just going to leave the crate by itself, right? So it's a 50 kilogram crate. That's its mass. You could calculate the normal force, right? Because you know the normal force in this case is simply equal to the weight. So if you can find the weight of the crate, then you know the normal force. You're gonna increase the applied force that the person exerts to the right. I would start at 100. So if you use the gross adjustment here, go to 100, and then start slowly increasing. See how my applied force is like 106. The frictional force is also 106. Sum of force is 0. Right now, what type of frictional force is this? Well, this is a static frictional force, right? And it's increasing to match my force. But at some point, and you have to keep increasing this, you'll find it, at some point, the cart will start moving. So you just increase it by 1. And then when a cart starts moving, then you know that 1 less than that must have been the maximal static frictional force, right? So you keep increasing. At some point, it'll start moving. So it's moving now. If I did that slowly, and I don't want to give you the answer, so I'm doing it quickly, but if I did that slowly, 1 less than when it starts moving must be the maximal static frictional force. So that will allow you to calculate mu s. If you know the maximal static frictional force, and you know the normal force, you can calculate mu s. And now once it's moving, right, see how the applied force is increasing, which the net force is increasing, but the frictional force is staying constant. Why? Because this is just now the kinetic frictional force. Once it starts moving, it doesn't even have to be moving at a constant velocity. We did that to find it, but if it's moving, then it's going to have a constant kinetic frictional force. In this case, you can read off that value. We know that the normal force, we can calculate the normal force. So this will allow you to calculate mu k, right? If we know the kinetic frictional force, we know the normal force, you can calculate mu k. All right, so that's it. It's a very simple part of the experiment with the simulation. You're just ultimately going to calculate mu-s and mu-k based on those two conditions. Okay, and then as I just described in that video clip, the last part, again, it was an older video, so I want to make sure that there's no confusion here. It's the same exact experiment with that simulation from the PHET group. And all you have to do is fill in the two values for mu-s and mu-k in this table. And then make sure you show me those calculations. Okay, so this is, I'm calling it question 1 because this is not in the lab manual. And then that's it. So that will be it for the friction lab. Thank you.